Today we'll be talking about forces round 875, Division 1 problem A, or this is also the Division 2 problem C. So here's a problem. I'm not going to go read it out loud, so feel free to pause it and read it. And let's pull out our trusty Microsoft Paint to do some experimenting with how to solve this. So first thing we ought to notice, you see that n is 2 less than or equal to n. So here we have 2 times 10 to the 5 is the max n. And this 2 times 10 to the 5, what that kind of tells us is that a brute force solution, if you look at this, and while like a brute force solution of just keep adding edges until until there's no more edges or no more vertices to add. If we just do that brute force, that'll give us a time complexity of O of n squared, which is way too slow for this input. And so this input suggests that we need some sort of maybe O of n log, maybe n log n. N log n might be pushing it a little bit, but here we have to come up with a better solution. And so credit to Alex and Gil for the problem, or sorry, Alex for the problem, and then for the write-up of the solution too. Here, one of the hints that we can start out with is by considering if n equals 3. Well, n equals 3, we really have 2 different cases, right? So we already have a 1, we know that for sure, and then we have a 2 and a 3. And we have the first case where it just takes 1 pass to go through. So for example, you go from 1 to 2, or like, for example, the vertices may be something like this. Maybe make it like this to make it. Could something be like 1, 2, and then 2, 3. Right. So this would only take 1 pass. And we can actually note that let's actually write the other thing first, the other case. So of course this is not the only example. Of course these edges aren't the only example. For example, it could be here to here, or like here to here, but this is just, it simplifies down to 2 cases. But the other 2 cases is like 2 and 3. Well, before you get 1 and 2, you can't connect 1 to anything. So let's say these 2 are connected, but then this edge is added afterwards. So for example, if it was something like 2, 3, and then let's say 3, 1, right? We have to do this in 2 readings because 3 only gets added to 1 on the first reading, and then 2, 3 has to get added on the second reading. So if we think about it, this is 1, and this is 2, right? And what's the difference between the 2? Well, first of all, we can quite easily see that this or whatever variant of this connecting the 1 appears either first here. If it appears before the 2, 3, then we can add that, or we can add the 2, 3 along with it on the same reading. But if it appears afterwards, we can only add this 1, 3, and we can only do this after the second reading. So this is number 2 that we can add it. And so how do we generalize this to multiple for there's more than n equals 3? Well, let's use dynamic programming, where we have dp I equal to the number of readings. I'll just call it R. And then we'll have to keep track more of the number of readings, obviously, because we have to keep track of when it was read. Like we saw before, like the 1, 3 coming afterwards makes it 1 more compared to the coming before. So let's call this, rather than using I, let's change this to say U. And then let's call the position where it was first read, like something like position. And this is the position in the list of edges. And so this is when it was first encountered. Well, you know what I mean. Okay. And so now that we know this, how, like, again, let's think about, let's go back to DP. So these states represent when they were, like, how do we use an old state to calculate a new state? Well, to think about DP, if we have an edge UV, right? And let's say U is already added, is already connected to, let's say, 1. Well, if V, if this edge, first of all, V could either be the same as DPU, right? So V could be the same as this U. It goes on the same reading. So, and the only case where that would happen is if IU gets read before UV. Right, and then that way we can put it in the same reading. And then, yeah, so, and then another case is that the UV edge gets added before the IU edge. But that would just mean we just need one more reading. So we have, again, two cases. Case 1 would just be DPU, or sorry, DPV is equal to DPU, while case 2 gives us DPU, or sorry, B equal to DPU plus 1. I'll just get added on to the next reading. How do we differentiate between the two? Well, again, like we said, index, right? And so this happens when the index of DPV is, well, it has to be like before. So let's say less than or equal to, so this index of the edge, so we'll call it IDE, the index of the edge would be less than or equal to the index that we found U at. And this would occur if the opposite were to be true. So it's greater than. Oh, sorry, I actually mixed it up. So actually, this would be true. It won't be for here, but that'll be a condition for 2. And then for 1, that would only occur when it's greater than. All right. And so how do we even get to these edges? Well, simple idea. We can perform DFS starting at 1. We have a tree, so every time we visit something, a tree, there's no cycles guaranteed, and so every time we visit something, we could just get away with DFS. Every time we visit something, we'll process it, and we just have to process it once. And so the initial conditions of DFS, we would set DP of I, or DP of 1 to be 1, so it's because you need 1 reading to get to step 1. That's the initial one. And then we'll say the ID of 1 would be like 0. It comes before any of instructions. Okay. Yeah, so let's try to put this into implementation. So we have this. Let's put a couple of constants in. So n is going to be less than or equal to 2 times 10 to the 5. So just for simplicity, we're going to be max n, or we'll set it to be 2, 5 plus 1. And then we can create both our DP arrays. and ID arrays of size max n. Okay. And finally, let's create our adjacency list. So we'll create a vector of pairs. And just another reminder, how do we get this index of the edge? Well, we have to record this somehow when we're going down through the list and like processing these edges. Say this is 1, 2, 3, 4, and so on. And so we actually have to store more than just the connecting edge, but also the like when the edge occurs. So we'll have to make this a pair of ints. And then we'll call it the adjacency list. And of course, there is going to be max n. Okay. So this reads fine. Let's just solve. And so first we have to read in the first number, which is going to be n, single integer n. So let's read that in. And then we have to clear up these arrays since we're using them as global arrays, and there's more than one test case. We have to clear them first. So let's do that. To n. 0. And of course, we have to clear the adjacency list. So let's do that and clear it out. Cool. So now that we have a blank slate, we can read in the values. So the values are going to be u and v. We're going to read that in multiple times, where this time it's from I to n minus 1. Because we have n minus 1 edges. And let's add that into the adjacency list. Whoops. Let's read that in first. U and V, adjacency U, switch back. This time, right, we have to record the index, so I, and then we have to record the actual vertex V. And we can do the same with U. Let's do that. And yeah, so now we've built our adjacency list. We can now go ahead and solve it. So first of all, let's set our base case, which is dp 1 equals 1. And then, oh, also, one thing I forgot to mention, how do we actually know the answer in the end? Well, the answer in the end, each one of these DPs are going to connect, like the DP array is going to have all of the values in it. So this would mean that the largest in that DP array is going to be our maximum. And so we'll do a DFS on this. I'll put that function in later, but for example, our answer, it will just be iterating through the array. So 1, 2, and DPI, and we'll just print that out. Okay, and so now it's the time to do the meat the section, and we'll do the DFS. So let's do that. Let's add our DFS method. Take an int, call it, I don't know, the current node we're on. Okay. And then all we have to do is to go through the adjacency list for that node. So let's do for pair. Put I in adjacency list of n. So let's call like I would be, remember I was our first value. So, oh, I guess let's not call this I then. Let's call it P for the pairs. Call this I, so P dot first. And then since it's the other edge, maybe let's call this U just to make it less confusing. And then we'll call, that's why we can call the other side D, which would be P dot second. Let's also call this U. Okay. So now we have to check if we haven't explored it yet. How do we know we haven't explored it yet? Well, DPI is 0. So if DPI, not DPI, basically if it's equal to 0. And then all we have to do is to go ahead and do what we said. Okay, so first of all, we're comparing the index, or how do we know which one we're taking? Well, first, let's compare the indices. And so if V is, or so let's just do this, V is going to be dp of U plus something. So if this index of the edge is going to be less than or equal to index of U, then we have to add 1. Really, I say less than or equal to, but there's never going to be a case where it's going to be equal. Never mind. So dp, or sorry, ID of U, I is less than ID of U. Yeah. Yeah, so next we set our ID because we've added V and we know where it came from. So let's add it just to be the I, and then we can just call DFS on V. Cool. So I've already added the sample test case, and this should not have been I, it should have been V. Yes, that's what it was, I think. Try this again. Oh, there we go. So 2, 3. And there you have it. Again, we can always just try and submit it just to double check. And there we go. It's accepted. Thanks for watching. I'll see you in the next one.